Hello, everyone, and welcome to the Jamb Physics in 40 Days series. This series is brought to you by Oya Learn, where we believe that when you dedicate within 30 to 45 minutes of your time daily, you'll be well on your way to acquire all the necessary skills to be able to ace Jamb Physics. So, if you are a student preparing for the Jamb exams, this video is particularly for you, especially if physics is one of your subject combination. So we'll be looking at a lot of topics that are in the JAM syllabus, solving them topic by topic and getting you prepared. Also giving you tips that will be very useful to help you solve your questions faster and also get better understanding on how to ace JAM physics. So this is day 9 where we'll be looking at elasticity. So if you're seeing this video for the first time, please do well to check out our videos from day 1 up until day 9. Trust me, you do not want to miss any of those videos. They are fully loaded, fully packed for you to get everything that you need to do well in your JAM exams. And also do not forget to share the video, like them, and also subscribe to the channel. When you subscribe, you help us to be able to make more helpful content like this, and you can also click the notification bell icon so that every time I put out a new content, you will definitely be alerted. Now, as far as elasticity goes, what JAMB expects every candidate writing the exam is stated here. They expect that you should be able to interpret the force extension curve. Now, when you place a solid material under stress, there's something called the force extension curve, which is a graph with the force applied on the vertical and the extension observed on the horizontal, right? So when you see such graph, there are some things you should be able to identify there, such as elastic limit, yield point, break point, plastic region, and the likes like that. So you should be able to interpret it, be able to identify those points within the graph. That's what this first line indicates. Now, secondly, they expect that I should be able to interpret Hooke's law and the Young's modulus of a material. Now, Hooke's law states that the force applied is directly proportional to the extension observed, provided that the elastic limit is not exceeded. So you should be able to state the law and also give the mathematical representation, which is F equals KE, where F is the force applied, E is the extension in the direction of the force, and K here is known as the elastic constant. Now, aside that, you should also be able to relate this with Young's modulus, where Young's modulus is actually what we use, is a coefficient used to test solid materials to see how elastic they are. Now, Young's modulus is actually a ratio of stress to strain. And you should be able to break this down further because stress itself is actually force per unit area, while strain is extension over original length. And if you put this into this, you then see that the Young's modulus can then be given as F multiplied by L over area and then multiplied by extension. So you should be able to apply all these equations when you are solving problems, especially with elastic materials. Now, another thing that they expect is that you should be able to use the spring balance to measure force applied. Now, oftentimes when you do not have any other thing to measure the amount of force applied on a particular material, you could use a spring balance if you know the spring constant of the spring in that spring balance. So there are relationships there which are also in these formulas that I've stated that you can then use to derive any part of the formulas here. And then finally, you should be able to determine the work done in an elastic spring or elastic string. Now, work done in elastic string is given by W equals average of force, so half force times extension. However, when you compare it with this equation that we have here, we can always substitute. That is, this can also be given as half KE squared, or it be given as 1 over 2 F squared over K. So any of these three equations works to find the work done in an elastic spring. It is also the equation that we use to find the energy. Alright, so if you're looking for energy, work done and energy have similar equations. They have similar dimensions rather. So because of their similar dimensions, the equations are also the same. So because of this, we can also use this to find the energy in a spring. So having gone through this, I think we should be well on our way to solve problems now from the Jamb past question. So get your materials and let's solve some questions. This question from the 2002 UTME says, the diagram above shows the force extension curve of a piece of wire. The energy stored when the wire is stretched from E to F is, so let's look at the diagram and then try to interpret it. So we can see that when the wire is stretched, right, by the force in newtons, it extends from this point here, which would be 0, all the way to Q, where the elastic limit is. And then we see the plastic region and the breaking point at R. Now, the question itself is asking for the energy stored in the wire from E to F, when it is stretched from E to F. So that is our concern point is E to F, which is this point here, right? So when we consider that, we see that at E, the force applied at that point is 0.1 newtons, and the extension at that point was 0.05. So this will be the start length that we're going to be working with. And then at the final length where we have F, we see that at that point the force has gotten to 0.2 newtons, and the extension is now 0.10, right? Now, applying the knowledge we've gotten so far, we know that the energy is same as work done, as I said at the beginning of the video. So the energy stored would therefore be half force multiplied by extension. Now, this will be 1 over 2. Now, the force applied will be the difference between these 2 points here. So we put that here, 0.2 minus 0.1. Then multiplied by extension, which is between these 2 points also. And that will be 0.10 minus 0.05. Now, this will give us 1 over 2 times, the difference here is 0.1 and the difference here is 0.05. Now, when you multiply this, you get 2.5 times 10 raised to the power minus 3. And energy is measured in joules. So the correct option in this case is option B. Now, in this question from the 2008 UTME, we're told that a spring of force constant 500 Newton per meter is compressed such that it shortens by 5 centimeters. So we have to find the energy stored in the spring. And earlier in this video, I did mention that when you're finding energy, we can apply the same equation as that of work done. And I said work done is average of force times extension. But in this case, you see the force is not given, but we are given the force constant. So you see, that's why I gave multiple equations in this case. Because this is the same thing as half ke squared, which is the same thing as half f squared over k. So in this case now, we just have to apply the ones that works for this question. So since we have the spring constant k and we have the extension e, we're going to use half ke squared. So the energy would then be 1 over 2 multiplied by k, which is 500 Newton per meter, multiplied by extension. Now, this is something you need to always know, that when you're solving problems in physics, most times you have to be very careful about the SI units provided, right? So like in this case, you see we have Newton per meter, and extension is given in centimeters. So they have to be in the same unit for this to work. So we have to convert this to meter, and that will mean that we are having 5 divided by 100. And remember, it is e squared, so we're going to square this. Now, this would imply that we have 1 over 2 multiplied by 500 multiplied by 25 over, now 100 squared will give us 10,000. Now, working with this, what do we get? So you can use your calculator to complete this, and this will give you 0.625, and energy is measured in joules. So the correct option of all the options provided is option A. Let us find the work done on a string which is extended by a mass of 10 newtons by 1.2 centimeters. So in this case here, we see that the force applied is 10 newtons. We see that the extension is 1.2 centimeters, which is 0.012 meters when we convert that into meters. And with this now, we can then go on to find the work done. So work done becomes the average of the force, so multiplied by the extension 0.012, right? Now, when you divide this by 2, we'll be having 10 multiplied by 0.006. And when we multiply this will give us 0.06 joules. But the answers provided are in standard form, so let's bring this to standard form as well. So this will be 6.0 times 10 raised to power minus 2 joules. That is what we have in option A. If a wire 30 centimeters long is extended to 30.5 centimeters by a force of 300 newtons, find the strain energy. Now, many students get confused by the word here, strain energy. They think that they are asked to find the strain, which would be force per area, but in this case, no, we are still referring to the energy stored in the wire. So, let's go on to apply the same equation, R force times extension. So, in this case, we see that the extension is going to be 30.5 centimeters minus 30 centimeters, which would give us 0.5 centimeters. Now, as always, we have to convert this to meters, so we say E equals 0.5 over 100. Okay, so now let's find the energy. That would be 1 over 2 times the force is already in newtons, so multiplied by 300, and then we multiply that by 0.5 over 100. Now this here one, here it goes 3 times. So what we basically have here is 1 over 2 times 3 times 0.5, which is also 1 over 2. So the energy is 3 over 4. Which is 0.75 in joules. So the correct option to go for here is option A. This question from 2009 UTME says, the diagram above represents the graph of force F applied in stretching a spiral spring against the corresponding extension X. Now the force constant of the spring is, now to get the force constant from the graph of force against extension, we have to find the slope of that graph, because the force constant is the same thing as the slope of the graph. They are equal. So let's look at the graph we have here. We can see that when the force of 40 is applied, the extension is 2 in meters. When this is 80, what we have here is 4. When this is 120, we have 6 as the corresponding extension. So let's go on to find the slope. So force constant K equals slope, which is y2 minus y1 over x2 minus x1, or as we will say it in physics, f2 minus f1 over x2 minus x1. So let's apply that. So we can pick your F2 at any point. So at this point, if I pick this point, what I will have as my coordinate here would be 6, 120. So, and I would like to pick the origin where we have 0, 0 as my next point. So if I apply that, that means my y2 this is my F2, which is then 120 here, minus F1, which is 0, all divided by x2, which is 6, minus x1, 0. Now what we have here is 120 divided by 6. Now don't forget that they have units. On this part here we have the unit of Newton. Here we have unit of meter. So if we break this down, what we have is 6 in 120, that would go 20 times. So we have 20 Newton per meter. So the correct option is option A. This question from the 1986 UTME says, The expansion of solids can be considered a disadvantage in the. Now, take note, this question is repeated over time severally in different years of Jamb. So it's one of those questions that is always recurring like that. It has showed forth in so many years like that. So let's look at where expansion of solids can be at disadvantage using the options provided. So option A says balance wheel of a watch. Now the balance wheel of a watch is a metal that is done to excise precision. It helps the watch keeps accurate time, and a small change in its length can affect the watch keeping time. So that is can cause it to lose time if it changes length, whether it expands or contracts. Now, in the case of option B, the fitting of wheels on rims, we see that wheels on rims are tightly packed, right? So when you want to pop off your wheel from the rim, or when you want to put it back on, you can use expansion as an advantage in that case, because when you apply heat, yes, it can expand and then make it tighter, and then when you cool it down, it contracts, makes it quite easy to pop off the wheel from the rim. Now, in the case of fire alarms, most fire alarms work by themselves, in the sense that as the heat from the fire heats up the metal in the fire alarm systems, it begins to expand. So when the heat gets to a certain amount, that is, the quantity of heat has gotten to a level that is considered to be dangerous, the metal would have expanded to the point where it clicks a switch or flips the switch and then notifies the fire department. So even when you are not around, when you're not at home, the fire alarm can go off immediately. It senses danger, and this is due to expansion in the solid. And then in the case of thermostats, you find the thermostats in your electric pressing iron. Once you connect it to the source of electricity, you can use it to iron, and then as you are ironing, that thermostat begins to expand. When it gets to a certain length, it will then cut off electric supply to the iron, thereby allowing the iron to cool down a little bit again before it continues to work back again. So this way, your iron does not exceed a certain temperature. That's why I see it's easy to set the temperature on your electric pressing iron. Now, you see, of all these options, B, C, and D are at advantage. The only one that is at disadvantage is A, because it causes the watch to lose time. So the correct option in this case is option A. Let's solve this question, which says a 50-kilogram block is dropped from a point 10 meters above as shown in the figure. Now, if the force constant of the spring is 4.0 times 10 raised to the power 4 Newton per meter, find the maximum compression of the spring, taking acceleration due to gravity as 10 meters per second squared. Now, before I go on to solve this question, if you're yet to be subscribed to the channel, please, I want to implore you to do so. When you subscribe, you're helping us to be able to create more helpful content like this, and it will just take you 1 second of your time. So please hit the subscribe button, and also don't forget to like and share the video amongst your friends. And in case if you have any question you would like us to solve, or any reservations you have concerning what we are doing, please put it in the comment section, and we will definitely attend to all of your comments. Now, that said, let's take a look at this diagram. So we have the mass. We see this distance is given as 10 meters, and it will come and then land on this spring. So there are two equations we have to work with at this point. So let's see them. There's going to be a work done by this material dropping, and that's the energy there, potential energy, right, which is mgh, right? And then we have the work done on the spring, which is half ke squared. So it is these two that we're going to equate, because they are both energy and work done. They are the same, they are equal. So, and this is because of the law of conservation of energy, which says energy is neither created nor destroyed, but it is transformed from one form to another. So you're looking at potential energy in this object, this block, being converted into the energy stored in the spring. So let's equate them. So we can then say mgh equals half ke squared. So the mass is given 50 multiplied by g, which is 10, multiplied by height, which is 10, equals 1 over 2 k. K is given as 4 times 10 raised to the power 4, that is 40,000, multiplied by e squared. So let's make e squared the subject. E squared therefore becomes 2 will come here, 2 multiply all of this, and 50 times 10 is 500 times 10, that's 5,000. 5,000 times 2 we have 10,000, all divided by 40,000. So we see that this cancel out, we have 1 over 4. So what this implies is that e is the square root of 1 over 4, and this will give us 1 over 2. So all the options provided are in decimal, so let's bring this to decimal. This will therefore be 0.5, and extension is measured in meters. So the correct option in this case is therefore option B. This 2021 UTME question says, if the stress on a wire is 10 to the power of 7 Newton per meter square, and the wire is stretched from its original length of 10 meters to 10.05 meters. The Young modulus of the wire is then, so to solve this, we're going to apply that Young's modulus equals stress over strain. And we already have the stress given, so let's find strain. The strain is extension over original length, and the extension is the difference between these two. So 10.05 minus 10, that will give you 0.05. Now divide this by 10. This will therefore be, now we can write this as 5 times 10 to the power of, now we have to move this 1, 2. And because it's divided by 10, to go one more time, so that will be minus 3. Right? So now we have 5 times 10 raised to the power minus 3. So let's apply this to find the Young's modulus. Now Young's modulus in this case will then be, now we have this as stress, which is 10 to the power of 7, all divided by, now this is 5 times 10 to the power of negative 3. Now if we resolve this, this is basically like saying 1 over 5, then times 10 raised to the power 7. Then when this goes up, it becomes positive times 10 raised to the power 3. Y therefore becomes, this will give us 0.2. Then this will be times 10 raised to the power 10. So we can then write this as 2.0 times 10 raised to the power 9. And Young's modulus is measured in Newton per meter squared. So the correct option in this case is option D. This 2023 UTME question says, a wire of radius 0.2 millimeters is extended by 0.5% of its original length when supported by a load of 1.5 kilogram. Now determine the Young's modulus for the material of the wire. Now in this case, the equation we're going to be applying for Young's modulus is that y equals FL over, and then we have AE. So let's look at the parameters we have. F is going to be mg, which is going to be, the mass is 1.5 kg multiplied by 10, and this would give you, remember this is in meter per second squared, this would give us 15 newtons. Okay, the length is not known, so we just call that L. Original length, let's call that L. And then L1, which is the new length, remember it is extended. Okay, let's say extension instead. Extension E is going to be L1 minus L, and that is actually, from the question, 0.5% of the original length. So we can say E is actually 0.5% of L. And 0.5% will give you 0.0. Now divide this by 100. That will be 0.005. multiplied by L. So 0.005 L. Now we have extension. The only thing left is area. So the area is pi r squared. Let's take pi as 22/7 and then we multiply that by r squared. Now r is given as 0.2 millimeters. So that would mean we have 2 times 10 raised to the power minus 4 if we are converting this to meters, right? And then we square it. So when you compute this with your calculator, you should get 1.27 times 10 raised to the power minus 7 meter squared. So now that we have done this, I think this should be 1.26 rather. 1.26 times 10 raised to the power minus 7. So now that we have the area, we have the extension, we have length and force, let's find Young's modulus. Young's modulus would therefore be F, which is 15, multiplied by length L over, now we have area, which is 1.26 times 10 raised to the power minus 7. And then we multiply this by the extension, which is 0.005 L. So L cancels L. Now we'll compute the rest with the calculator, and that would give us 2.36 times 10 to the power of 10 Newton per meter squared. So this is approximately 2.4 times 10 raised to the power 10 Newton per meter squared, which is the same thing we have in option A. Before I go on to solve this 2024 UTME question, if you're yet to subscribe to the channel, I would like to implore you to please do so. We really need you to subscribe to the channel, because when you do so, you are helping us to be able to make more helpful content like this. So please hit the subscribe button. To only take a second of your time. And also don't forget to like and share the video. You might just have someone on your timeline who really needs this video to help them prepare adequately for their next Jamb exam. So please like, share, subscribe, and you can also hit the notification bell icon so that you get alerted every time a new content is posted on this channel. Now, to solve this problem, we are told that the stress experienced by a wire of diameter y/pi in meters and loaded by a weight of y squared in newtons is, so we are to find stress, right? Solution. Stress is given by force over area. We already have the force here as y squared in newtons, so we need to find the area. Now, the area itself is given as pi d squared over 4. Now, this equation is similar to pi r squared, but because we are given diameter is why I'm using this particular equation. If we're given radius, I would have used pi r squared. So in this case, what we're going to be having here will be pi multiplied by d, which is diameter, y/pi, then we square that, all divided by 4. So from here we can then see that the area is therefore pi multiplied by y squared, all divided by, this pi squared comes down, so we have 4 pi squared. So this pi here cancels one of the pi, and then the area is y squared over 4 pi. That's area. So now let's go on to find stress. The stress is therefore force. The force is y squared, now divided by the area, which is y squared over 4 pi. Now when we change this division sign into multiplication sign, we can then go on to flip this fraction. So the stress is therefore y squared multiplied by 4 pi, all divided by y squared. So we see that y squared cancels y squared, so stress is 4 pi. And the unit of stress is Newton per meter squared. So the correct option in this case is option C. This question requires that we find the dimension of Young's modulus. So we know Young's modulus is force multiplied by length over area multiplied by extension. And the dimension for force is ml t raised to the power minus 2. So we're going to multiply that by the dimension for length, which is L, or divide by dimension for area, which is L squared. And then we multiply this by the dimension for extension, which is another L. So when we look at this, what we have is M, then L times L will give you L squared, and then this is t raised to the power minus 2, all divided by L cubed. Now from here we see we have M. Now L squared divided by L cubed, that is L 2 minus 3, that's minus 1. So we have L minus 1, and then T minus 2. And this is the dimension for Young's modulus. And that is found in option C. The property by which a material returns to its original shape after the removal of a force is called elasticity. Yeah, because when you apply force to an elastic material, it will cause it to change shape or increase in length, as well as also it could also decrease in length depending on the direction of the force. And the moment you remove the force from an elastic material, it will always go back to its original shape and length. That's why it's elasticity. On the other hand, ductility describes when a material is able to be stretched into a wire form like that without it breaking. Malleability would mean that the ability of a material to be hammered or pressed into a new shape entirely by the application of force. And plasticity is the permanent deformity of a material. Like for example, when you exceed the elastic limit of an elastic material, it could form it to become a plastic. In other words, plasticity, because the shape is now permanently deformed. So, but in this case, the answer is elasticity, which is option A. In this question, we are asked that the point beyond which a stretched spring does not return to its original length is called. Now, if you recall from definition of elasticity, said the ability of a material to stretch when a force is applied and then return back to its original shape or size after the force is exceeded. But there is a condition that must be followed for every elastic material. And that condition is that it is provided that you do not exceed a particular limit. Now that limit is called the elastic limit. So to define that elastic limit, it will be the point beyond which when you apply force, the material will not be able to return back to its original shape or size, which means the correct answer for this question, elastic limit, option B. A load of 5 newtons gives an extension of 0.56 centimeter in a wire which obeys Hooke's law. So what is the extension caused by a load of 20 newtons? So in this question, we see that we are maintaining the same wire, so which means that it's going to have a constant, the spring constant is going to remain the same for both applied force. So, and for spring constant K, that will be F over E. Now, what this implies is that F1 over E1 equals F2 over E2, since we're going to keep the same constant here. Now, the first force applied is 5 newtons, and in this case, the extension provided is 0.56 in centimeters. Now, when we equate this to F2, which is 20 newtons, let's find out the value of E2. Now, from here, we can say E2 equals 20 newtons multiplied by 0.56 centimeters, all divided by 5 newtons. So, newtons cancel newtons, 5 here 1, 5 here 4. So, what we have here is 4 multiplied by 0.56, and that will give us 2.24, and the unit here is centimeters. So looking at the options, the correct one is option C, so we go with C. This question says